Okay, here we go. Yes, I am breaking this into two lessons. Lesson 2.2, homework for tonight. All right. So even though we will talk about properties from algebra, that's an important part. The real important part of this lesson is your introduction on how to do proofs. All right. So really what I want you to do is learn how to do a two-column proof today. Before we do that, we're going to add some things to our book of truth. So in our book of truth, we're going to add some properties that we learned in algebra. Now, these are properties. We're not going to prove these. So these are properties that we've already used for many, many years in algebra. All right, so it will sound a little strange, but let's consider three variables, A, B, and C. And each one of them is a real number. That means any number you can think about, a fraction, decimal, positive, negative, including zero. So think about this. If I had three numbers, and we're going to put them in the form of a variable, A, B, and C. I'll start off with a true statement. I just chose the number five. It could be any number, but five clearly is equal to five, right? So if I give a little bit of space there, see what I just did, and I add or subtract or multiply or even divide something right there. For instance, if I add two, notice while the value of the left side and the right side change, now it says 7 equals 7, the equality didn't change. So the point here is that if you start with a true statement, 5 equals 5, and you add the same thing to both sides, you maintain the equality. You don't change, you don't maintain the value of the left and right side, but you do maintain the equality. Now, this is something you've learned many, many, many years ago. This should not be a surprise. So if we formulate this into a property, instead of using the specific numbers 5 and 2, we're just going to use some variables. So we're going to take those values on the left and the right that I just circled, and we're going to assign a variable to each one. So we'll say A can be equal to 5, and well, so could B. So now if I rewrite that equation right here, I would simply say A is equal to B. And then if I want to rewrite it with the second equation there, I need a second variable, we'll call it C. So if C is equal to 2, now if we rewrite that equation, it would say if A is equal to B, then A plus C is equal to B plus C. And all it's really stating there is that if you start with an equality, as long as you add the same value to both sides of the equation, you maintain the equality. And since we added something to both sides, that's why this first property to write down in your book of truth is called the addition property. So the addition property says if A is equal to B, then A plus C is equal to B plus C. These are going to come at you fast. You can always pause the video. So I'm going to move to the second one. Well, if this one is true, I won't show you the details. If this one is true, then so is subtraction. So second property is going to be called the subtraction property. So as you copy this one down, think about the following statement. Why are we writing down these properties? Well, remember, we're writing them down in our book of truth, and the only thing we allow in our book of truth are truths, things that we either have as a definition or a postulate or a theorem, or in this case, properties that we've used before. We use the things in our book of truth as reasons for statements that we make. So we don't just make a blind statement, we make a statement that is backed by the truth of either properties or definitions or postulates or theorems. So when I talk about a triangle in the book of truth, we will have the definition of a triangle, polygon with three sides. Don't write that one down. We haven't gotten that one yet. And that goes in our book of truth because that's the truth. So these properties are just going to be some more truths that we put in our book of truth. Well, if we have the addition property, we have a subtraction property. You guys have all solved algebra problems. Well, you know that there's also a multiplication property. So if A is equal to B, then as long as we multiply both sides by the same number, or the same value, or the same variable, we maintain the equality. We get different values on the left and the right, but the equality is maintained. And if we have multiplication, then clearly we must have division because we've divided both sides of the equation plenty of times. But we do have to add one extra rule, right? And that rule is that C cannot be zero. I know that I cut this picture off a little bit. That's a C there underneath the A and the B. But what this is saying is that the division property, if A is equal to B, then A divided by C is the same as B divided by C, as long as C is not zero. Remember, we can never divide by zero. So our first four properties are the addition, subtraction, multiplication, division property. This is going to seem silly, this one right here, but here it comes. If 5 is equal to 5, and I assign the variables for 5, well, then A is equal to A, right? If A is equal to 5, then I would change 5 is equal to 5 to A is equal to A. Now, this seems like a silly one that it's a property that A is equal to A. Clearly, if you are a number, you are equal to yourself. And the question is, why would I need this property? And oh boy, we'll be using this property plenty of times this year in geometry. We'll use it a few times in this chapter, but we'll use it a ton in the subsequent chapters. All right, so this is called, like if you look at a mirror, that would be reflective. This is called the reflexive property. And the reflexive property says that any number is equal to itself. All right, this one is also in yellow. Well, I'll explain the yellow here in a few minutes. Next property. So if 5 is equal to 5, and we assign variables A and B to both equal 5, we would get A is equal to B. All right, now what are we going to do with that? If that is true, then if I just flip that equation around, it would say B is equal to A. Now, we use this many times in algebra. For instance, if you're solving an algebra equation and you get to the final step and you have 3 is equal to X, right? You're probably more familiar with flipping around and saying that X is equal to 3. Now, you have done that for plenty of years now. And well, what gives you the ability to write that there is what this property is called. And this property is called the symmetric property. So the symmetric property, it's also in yellow. So if A is equal to B, then B is equal to A. And this gives you the ability to just flip an equation completely around. Right side is now the left side is now the right side. So we have the addition property, subtraction, multiplication, division, reflexive, and the symmetric property. I said these will come at you fast. Make sure you're pausing the video. All right, so think about this. All right, if A is equal to 5 and B is equal to 5, then clearly A is equal to B. If I make a third statement, so B is equal to another value, C, the question is, well, I didn't define C. So if I define C as also equal to 5, then everything's equal to itself. And therefore, since I'm not making any statements specifically about the relationship between A and C, based upon those two statements of there alone, if A is equal to B and B is equal to C, therefore I could literally say that A is equal to C. Now, I gave you those values of 5 over there on the right, but if I just had these two statements without, if I got rid of these three statements right here, it would not change the fact that A is equal to C. This particular property we use quite frequently in geometry, right? And this is called, let me erase that. This is called the transitive property. So the transitive property says if A is equal to B and B is equal to C, then A is equal to C. And just make note of the fact that the way it's written right here, that this value and this value will always be the same. In other words, between the word and are exactly the same things, a B and a B. And the result is that I'm trying to change colors here, is that this value right here is equal to this value. Hopefully that made sense. If it didn't, rewind the video, play that part again. If you still have questions, ask me again. I can explain it a different way. All right, so now I'll explain the yellow part. So both the reflexive, symmetrical, and the transitive property are in yellow. That's because not only do they work with equations, equalities, they also work with congruence, right? So for instance, if you have a segment, well, segment AC is equal to segment AC. And for the symmetric property, if segment AC is equal to segment, say, EF, then segment EF is congruent to segment AC. So all three of these also work with a congruency symbol. All right. Think about this. If I have a value for A, 5, and I have an equation that uses the letter A, notice that equation there on the right, C plus A is equal to 2 minus D. Then if I choose to, I can get rid of the letter A in the equation and replace it with a 5. So in other words, I can go to that equation on the right, and if I see the letter A, I can write 5. We've seen this before plenty of times in algebra. This is called the substitution property. The substitution property allows you to swap out a variable with a number. It also allows you, not just for numbers, to swap out variables with other variables. If A is equal to the variable B, then I could take that same equation there at the top right and substitute for the letter A, the letter B. So substitution works for numbers and it also works for variables. This is called the substitution property. And it looks like we're out of space. I do have one more property to write down. Um, Two of the most important used properties are as follows, right? The reflexive property and the substitution property are used quite extensively, quite extensively. It doesn't seem like we would use the reflexive property a lot, but we do. And boy, do we use the substitution property. Substitution property is probably the most used property that we will see in geometry. All right, on to our last property. So our last property is the distributive property. And well, that's why we call it the distributive property, because it's a property that we use frequently. So the distributive property we'll use many times in geometry, not as much as the substitution property, but we'll use it. I'm going to move on, but you can obviously pause the video and write this stuff down. All right, so that is for the property, that covers the properties for this particular section. What are we going to do with those properties? Well, they're now in our book of truth, and they will be used as reasons or justifications for these things that we call proofs. And so for the rest of the class here, we're going to talk about these things called proofs. So here we go. These will be the most challenging thing that we do this year. So the last couple classes, we had if-then statements, we had converse statements, we had biconditional statements. They were all statements. And we also made note that some of these if-then statements we've seen before in these theorems that we've copied down in our Book of Truth. And we made the statement that the things that we need to prove before we put them in our Book of Truth are those theorems. So we're going to talk about the process now of how to prove theorems. Remember, we don't prove postulates, we don't prove definitions, we don't prove properties, but we will prove theorems. Okay, so for all of these, right, we have to prove that they're true because all of these are going to be theorems, right? So we're going to prove them to be true. So how do you do that? So today's class is how do you prove things to be true? The basic idea is if we need to prove something is true, well, in real life, if you want to prove that something is true, you make an argument. I claim that, for instance, you are 14 years old, or 15 years old, or 16 years old. If someone wants to call me on that claim, well, I could provide a birth certificate. That would be an agreed upon set of facts that we would both agree that, oh, well, if you show me the birth certificate, then that is definitive proof of how old someone is. Okay. So in math, we do basically the same thing, right? We have some agreed upon facts. Those agreed upon facts, right, are how we prove things. So the argument that we make in real life is called a proof in geometry. And we still have agreed upon facts. Those are the things that are in our book of truths, right? We also need to make a convincing argument. And I will tell you that every time we do a proof, we will be making a convincing argument. Remember, to prove something wrong, you just need one counterexample. So I can't leave any space for someone to make a counterexample. All right. And remember, it's not a proof unless it is convincing. Okay. One counterexample ruins the whole darn thing. So when we talk about the formats for how do you actually write a proof, right? There are many different formats. Generally speaking, in high school geometry, we use a format called a two-column proof. And as the name implies, there's going to be two columns. There's also these things called paragraph proofs that we'll see later. There's also something called a talking proof. There's something called a coordinate proof, and we'll see all of those this year. You can have a picture proof where you simply draw a picture that convinces someone based upon the truths that are in your book of truth. They convince you of your argument. We'll see all of those this year. So now it's time to concentrate. We're going to do a proof, right? So don't get sleepy at this point. All right, so without a doubt, this is the most challenging. I'm not saying today, but I'm saying in proofs in general. We're going to be doing proofs until the end of the year, and they are the most challenging thing we do all year. So let's write down, not in our book of truth, but let's write down some facts about some proofs. First off, what is a proof? A proof is a logical way. Notice the key word there, logical. It's a logical way of showing that a conjecture is true. Remember, the conjecture are those if-then statements. So this is going to logically show in a convincing manner that a conjecture is true. And I said in high school geometry, we like to use the two-column proof. So we'll be using a two-column proof for at least a month before we see another form. So a two-column proof, you can write this down off to the side. We'll have, well, as the name implies, two columns. The column on the left is where you're going to make statements. The column on the right is where you justify or you give the reasons for each statement. And the reasons will be directly linked to your book of truth. You make a conjecture, you make a statement, how do you prove each statement? You cite something from your book of truth, right? You will be given two things in a proof. Like when they hand you the problem tonight for homework, you're going to be given something called literally the given, and you'll be told to prove something. So for instance, it will say given blah, 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 prove blah, blah, blah. It will make sense when we do an example. The statements will always start with the given. So given is your starting point. Whatever they give you, you're going to write that down as your first statement. And the reason for that is, well, it was given to you. You will you will argue logically, sequentially, in steps that make sense from one to the other one until you arrive at the proof part. And the proof part is the ending point of the proof, right? All the statements you put in the statements must be logical and they must be in a specific order that makes sense. You just don't put random statements down. And remember, everything in the reasons comes from your book of truth. So I'm going to introduce you to your first proof. And because you already know how to solve an algebra problem, I'm going to solve an algebra problem using a two-column proof format. So it will seem a little silly, and there's a few of these tonight for homework, but this is supposed to at least get you to grasp the idea of what a proof is. And that's why we use something nice and familiar here, an algebra problem. So this is what the problem will look like. Remember, they're going to give you two things. They're going to give you a given, and they're going to ask you to prove something. So we're given that equation, 4x minus 5 is equal to negative 2. And we're asked to prove, in other words, use some algebra and prove that x is equal to 3/4. So how do you do this? Well, first thing is you set up your two-column proof. So we make two columns. Column on the left is your statements. Column on the right are your reasons. We always start a proof with the given. So what's the given here? Literally, the given here is 4x minus 5 is equal to negative 2. So I write that. What's the reason? Well, that was given to me. So all proofs will look like this, just like this. You simply rewrite the given, that's your starting point, and the reason to justify the given is, well, that was what was literally given to you in the problem. Now, I'm going to show this next step. It's really not the second step, but we're going to make a bunch of statements until we arrive at the end. So when you see me do this in a class or on a video, right, I will always put the last statement at the bottom of the two-column proof. The space in between is where I put my statements. And so you might ask yourself, well, how do you know you've given yourself enough room? Well, remember, I made these slides. I know how many statements I need. So I will always have mine spaced with the right amount of space. You won't know how many statements you need to do. The reason why I always put the proof part there is so that we can at least visually see where we're going to. It's kind of like, you're keeping the finish line in sight, so to speak. Would I encourage you to do it just like this? Yes, but I would put that x is equal to 3/4 literally at the bottom and bottom of your two-column proof so that you have enough space because you might not know how much space you need. Okay, so now what's left to do is to reason logically, in other words, make statements until we arrive at the prove part. So let's see, it's an algebra problem. If you were presented with that algebra problem, what would be your first step? And hopefully you're screaming at the screen and you're saying, I would add 5 to both sides. Okay, so let's add 5 to both sides. If I add 5 to both sides, I'd get 4x is equal to 3. But I got to justify that step from the book of truth. So what property do we have that if you start with an equation allows you to add 5 to both sides? Well, hopefully you know the answer to that. That's the addition property. So I simply write addition property. Okay, so that line is done. Now I need to move from the line of 4x equals 3 to x equals 3/4. In other words, what step would you do? Well, that would mean I would divide both sides by 4. If I divide both sides by 4, I would be left with x is equal to 3/4. So I just need to justify that step. What step allows you to, or what step justifies you dividing both sides by 4? The division property. And look, I've reasoned logically from the given to the prove, and I just proved that x is equal to 3/4. We have a formal way of ending a proof. It can be done one of two ways. You can either use the letters Q, E, D with periods that stands for something. I'll show you the next slide. Or you can simply put a square. And so either the square or the letters QED capitalized with periods, that's how you end a proof. Okay, so what does QED mean? It's Latin for quod erat demonstrandum, which means that which was to be shown. I was asked to show that if I give you 4x minus 5 is equal to -2, I can show that x is equal to 3/4, and I did that. So I can write QED. You can also put a square. Yay, we did our first proof. Now we are in geometry, so even though they're going to give you some of those algebra proofs for practice, that's simply to get you used to this method. Let's do an honest to God real geometry proof. So here's your first honest geometry proof this year. All right, we're given a bunch of information there. Let's see, we're given that we have two segments, RT and PQ. They intersect at S, and they intersect in such a way that RS is equal to PS and ST is equal to SQ. And we're asked to prove that RT is equal to PQ. In other words, we're asked to prove that RT has the same distance as PQ. All right. Well, you're on. First step is always rewrite the given. Now you notice I left off the intersect at S part, but I have everything else there. The reason is always the given. Okay. And we need to reason logically until we get to that statement. So if you do this, you've at least started the proof correctly. The hardest part about any proof is the second line. In other words, the line that's going to go right here. This is always the hardest proof. So I'll give you a couple pointers. Point number one, in order to kind of figure out what the statement is, I always look at where I'm going. So somehow I need to get a statement that has the letters RT in it and PQ. So I look back at the shape over here and I try to identify RT and PQ. And if I notice, RT is this entire segment right here. And PQ, well, let's see, PQ is this segment right here. So I'm asked to say something about those two segments. I'll erase all that mess. And let's see if we can say something. Now, I usually ask people to look at the picture and tell me something smart about RT. And after a while, this will come very naturally, but at first, this is really challenging. Look at RT and say something smart. Well, if we think about all the stuff we've learned about segments, one of the things we've learned about segments is the segment addition postulate. And the segment addition postulate states that one piece plus another piece equals the whole piece, or the small piece plus the medium piece equals the whole darn thing. So I could say that RS plus ST is equal to RT. And for PQ, I could say that PQ is equal to QS plus PS. And so I'll state that right there. Notice that's two statements, and each statement is separated by this semicolon right here. So you can make as many statements as you want per line, right? Hopefully they fit there, as long as the reason is the same. If you have a different reason for a statement, then make it a separate line. But notice I just made two statements. I said that RT, the whole darn thing, is equal to RS plus ST. That's a segment addition postulate. And I said that PQ, that's the whole darn thing there, is equal to PS plus SQ. And the reason, segment addition postulate, or postulate 2. Abbreviations are fine. Instead of writing the whole word postulate, you could put POST period 4, or segment addition postulate. Now you can kind of see why we want to have things in our book of truth, because you got to remember all these postulates and theorems and definitions and properties. Okay, so let's see. What should we write next? Well, as I look this over, I notice I have an RT here and I have an RT here. RT here. Why is this not drawing? I have an RT there and I have an RT there. Okay, there it goes. Notice though I have a PQ here, but I don't have a PQ up here. I have an RS plus ST. So maybe if I could change that around just a little bit. So I'm going to try to change that RS plus ST. And if you notice, if you look directly above, in other words, right here, it tells me something about RS and ST. What does it say? Right? Well, it says that if you see the letters RS, in other words, segment RS, you can erase that and write segment PS. And if you see segment ST, which I do, you can erase that and replace it with SQ. That's called a substitution. So that's what I'm going to do. I'm going to substitute for RSPS and substitute for STSQ. Now the question is, why would you do that? Well, kind of looking at the bottom, I'm trying to think at least a step or two ahead, just like when you played checkers or chess, to see if I can make the right move. Is that going to lead me to the answer? And notice, okay, here we go. This is a lot of noticing, right? Notice that if we look directly above to right here, it says that PS plus SQ is equal to PQ, which is the letters that we wanted for the right side of our equation. So now I got to justify that statement. That was the substitution property. But now to go from the step that's literally right here, to go from this step to this step, I'm simply going to replace PS plus SQ with PQ listed right here, because that's what it says. It says PQ is equal to PS plus SQ. All right, so I do that. So I replace that with that, and the justification for that is substitution property. So hopefully that was a convincing argument to you. If you're very intimidated, many students are at this point, you got to trust me when I say the more of these you do, the better off it will get. So we end the proof always with a QED or a little square, and you've done your first geometry proof. Congratulations. All right. Proofs are the most challenging thing we'll do this year. They will be very challenging. There will be a proof on nearly every single test, if not two proofs on every single test. Proofs separate A and B students. If you can't do a proof, you're not going to get an A in this class. You have to be able to do a proof in order to earn an A. You can pass the class with a B if you're not very good at proofs, but in order to get an A, you're going to have to be good at proofs. And you're just going to have to trust me when I tell you that they will absolutely get easier the more of these you do. As I record this, remember I'm about a chapter ahead of you right now. As I record this, both of my classes, the average class and the honors class, the first couple of days they were very hesitant and they were kind of worried. And then we get day 3, day 4 of doing proofs, and many of them now are like, okay, they're not that bad, right? But I will say they will be the most challenging thing we do this year. Okay. Some students are really good at proofs, and some students are really bad at proofs. And so don't judge your ability on how quickly you understand this. In other words, if somebody gets proofs very quickly and it takes you 5 extra minutes, well, as long as you get it, it's perfectly fine. All right, we'll do one more call today. All right, so here we go. So let's see. I look at the shape first before I read anything. It looks like we got a bunch of angles. I got angle 1, 2, 3, or if you want to call them by letters, AOB, BOC, and COD. Let's see. The given is that angle AOC is equal to angle BOD, and we're supposed to prove that angle 1 is equal to angle 3. So as I look at this proof, the first thing I think about is, well, where are we finishing up? We're finishing up with the measure of angle 1. So I really want a statement that has something with the measure of angle 1. So I go to my picture and I look at angle 1, right? I'm also looking at the given. The given says something about AOC. And if I trace AOC out, I don't know how well you can see this, but if I trace AOC out, it's this big angle right here. And this big angle is made up of both angle 1 and angle 2. So I could clearly say the following statement, that angle AOC is equal to angle 1 plus angle 2. And then I got to erase this. Then I could do exactly the same thing on the other side with angle BOD. So angle BOD is right here, and angle BOD is equal to angle 2 plus angle 3. And that was the statement that I just made. Now, how did I know to make that statement? Once again, I'm kind of looking where I'm going. Where am I going? I'm going way down here to the measure of angle 1. So I need to have at least one statement that has the measure of angle 1. Well, I also have the measure of angle 3, so I need another statement that at least has the measure of angle 3 in there. And so that's my thinking. All right, justification. Well, what justification is that the larger angle is equal to the two of the smaller angles? It's like the segment addition postulate, but it's called the angle addition postulate, postulate 4. Okay. Now I've highlighted in red there that the given that AOC is equal to BOD, and what I want you to pay attention to is the fact that I've got AOC right here, and I got BOD right here. And the original given statement says that those two are equal to each other. So I could set them equal to each other. I mean, I could write AOC is equal to BOD. I'm just going to choose to write the other stuff, the stuff that's to the right of both of those statements. So instead of repeating the given and saying that AOC is equal to BOD, I'm going to say the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 2 plus the measure of angle 3. So all I'm going to do is put those two statements together. Pause the video, rewind it until that makes sense. Okay, justification for that, I'm doing a substitution. I'm substituting for AOC 1 plus 2 and for BOD 2 plus 3. So that's a substitution property. All right, looks like we're almost done. We just need a justification for the ending, and I would just ask you to draw your attention, right, to the statement right there. And notice it says the measure of angle 2 on both sides of the equation. Remember, the measure of angle 2 is truly just a number, right? I don't know what the number is. I haven't measured it with a protractor, but it is the same number. 2 is the same as 2. So therefore, I can subtract the same thing from both sides using the subtraction property, and that would get rid of the measure of angle 2. Therefore, the measure of angle 1 is equal to the measure of angle 3, QED, quad erat demonstrandum. That which was to be shown, we showed. Did that make sense? Hopefully. Okay. As you're doing the proofs tonight, just remember some students are really good at this, and some students will struggle for the first week or so of doing proofs, sometimes even the first month. Our goal here is to understand what a proof looks like, the process, and we will work really tirelessly on those statements, right? Because the statements are usually challenging. I will give you, just a quick note, the difference between the substitution and the transitive property. So this is your classic transitive property. If A is equal to B and B is equal to C, then A is equal to C. Notice how that's written. That's a transitive property. Substitution, right, would look like this. If you start off with an equation where A is equal to B plus C, and you're told something about B and told something about C, and if you rewrite those variables with the new variables, you're doing substitution. So that's really the difference between transitive and substitution. I usually get some student ask, what's the difference between transitive property and substitution property, right? So that's it. Don't panic, right? For the proofs they're going to ask you to do, we say have training wheels on them, right? If we look at the proofs, they're going to look something like this, right? Where they basically do the entire proof for you. They just leave some blanks. So this is a classroom exercise, not what I'm assigning you. And just remember, the first reason for any proof is the words given. Oh, that was easy. It's harder to write with a mouse than it is to write with a pen, and I don't have a pen. You're going to logically reason logically, except they're giving you the statement. So there's no reasoning logically. You just need to justify each step. So in other words, for homework, you're filling in these blanks right here. So just think about your properties and then think about your postulates, because we really only have mostly postulates and a few definitions, 3 theorems, and a whole lot of properties. So that's what homework's going to look like, and it would not surprise me if you struggle a little bit at this, but give it a shot. And that will do it for today. Once again, here's your homework, and I will see you in the next class.